All right, so let's get started. So last time we talked about factorization in the effective theory, and there was one type of factorization, which was this hard collinear factorization that happened when the Wilson coefficient, which is a factorization between sort of the low energy physics described by the operator and the Wilson coefficients. And we decided we wanted to think about that in the following way, as having convolutions between variables that appear in the Wilson coefficients and variables that appear in the operator. And the way that we can think about that is just what the most general possible thing is that we can write down for the Wilson coefficients. And of course, it can depend on large momenta. And so large momenta here includes the label operator. So large momenta always show up in the Wilson coefficients. And in this case, that includes momenta that are the large component, the order lambda 0 component of collinear fields. So this is hard collinear factorization. And it just comes out in a kind of natural, standard way in this effective theory because we've set up the effective theory to have the right low energy degrees of freedom. So even though it's a little more complicated than just a simple product, we see sort of what the variables are that can connect the two things just by power counting, essentially. That the large momenta are the ones that are order lambda to 0. We can kind of do this generically if we recall the definition of our Wilson line. You can see how this would carry over to a generic case in the following way. So that was one way of defining the Wilson line. And as an operator, we had relations as well. So we had this relation, and in particular, we could take this to any power, and that just takes the p bar to any power, like that. So you can really think of this as, given any function of this operator, im bar dot d, you can always write that as a Wilson line, a function of p bar, and a Wilson line. And what you want to do is you want to stick these Wilson lines in the operator, and you want to put this function in the Wilson coefficient. So you could think, let me start with operators where I can throw in im bar dot d's because these guys are order lambda 0. These are the collinear derivatives. I'm just allowed to stick as many of those as I like in my operator. But given that I put in any function of them, I could always do this. And the right way of thinking about it is that this function here is what is determined by matching. It's your Wilson coefficient. So. And that's what we were effectively doing up here. But this is, in some sense, a more general discussion. You can see that even if you had multiple places in the operator where you could insert these derivatives, then you would just do this. And what would happen is at the end of the day, you get a function of all the possible large momenta that you can form from the operator. So maybe one more line. So think of it that you can always separate out. You can always separate out that, make a split like we did over there with the integral over some variable, and then leave something that you can stick in your operator if you make it like this. So this could go in the operator, and then that's the coefficient.
If I stick this in up in that operator, that actually wasn't good.
Well, here I didn't write it. So if I wanted to put in im bar dot d's, I'd stick them between. right? If I wanted to have used the formula, if I wanted to use this kind of logic, I wouldn't have written this. And I would have said let me stick an arbitrary function of im bar dot d in here.
But before you even write
It
down...
has to be between them because of the gauge invariance.
Right, so before you even write down the Wilson line, so say you start to say, okay...
Oh, yeah, so there's still, right, this Wilson line here, right. This Wilson line here came from this h. So that's still going to be true. And what I'm saying, if you think about this operator, right, I could dress it up by putting any function of im bar dot d's right in here, because that would still be an same order and gauge invariant.
Okay, but this is an alternative.
But then if I use this, then if I use this formula, it would sort of push this w, that would cancel there, and then this w comes back, and then you get the f. Okay. So in general, the right way of thinking about this is as follows. We can encode this in some notation. By just setting up a convenient set of building blocks, which are gauge invariant objects under the collinear gauge transformations. And so we need to have a fermion field, but we know that the fermion field, generically, we can make it gauge invariant by multiplying by a Wilson line like that. And because of this, what we were just discussing here, generically we can be, in our Wilson coefficients, sensitive to the momentum of this object. And so we can denote that by defining the following thing. Which is just a chi field that carries some momentum, which is the overall large momentum of this product of fields. And sometimes this guy goes by the name of the quark jet field, because it's kind of the object. If you were to produce a quark in a hard scattering process, the quark would be represented in your operator by this W dagger C. The Wilson coefficients would talk to that quark through the large momentum. And that quark in the low energy theory would evolve into a jet. So it goes by that name. You could also think of it as a parton field, because as it turns out, and as we'll talk about later on, if you were to think about the parton distribution function and what pulls a quark out of the proton, it's exactly this operator. And then that quark's momentum, what momentum that quark carries, is exactly picked out by this delta function as well. So these are the objects we'll actually usually want to work in terms of. We can do something similar for the gluon, which is a curly B. And I'm going to define it. If we wanted to get a gluon, the natural thing is to use a field strength, because then you get a gluon without any derivatives. But I want my object to be dimension 1. So I'm going to define it in the following way. So here's a field strength, commutator of covariant derivatives. These are collinear derivatives. And I throw Wilson lines around it to make it gauge invariant, and then to make it dimension 1, I throw in a 1 over p bar. And if you start expanding this out, then the first term will be the an perp gluon, and so this B just has the an perp gluon in the same way that the first kind of order term in this chi is just the fermion if I set the Wilson line to 1. Okay, so it's starting out as a perpendicular gluon, but it's dressed up in a way that makes it gauge invariant in dimension 1. And then, just like we did here, we can put a subscript on it with a omega to say that we fix the large momentum of it. And sometimes there's a convention that that's done. You have to decide if you want the Wilson line, I mean the delta function, to be a W minus P bar, W minus P bar dagger. Anyway, it doesn't really matter that much, but it's just a sign, because it's just a sign of what you mean by a W. If it's an outgoing gluon, this is a more convenient convention. Okay, and so this delta function here and this P bar here, when I put these square brackets, what I mean by that is that they don't act outside. They just act on the operators inside. So these are objects that exist by themselves, and they don't care about other things that are multiplying them later. So that's the gluon analog of the quark. So it turns out that we can show the following, that if you want to build operators that are subleading order, a complete set of things to do that is as follows. It's this chi-n, the bn perp, and then you could also need p perps. And then you could also have ultrasoft fields, where it's really kind of similar to how you're used to building operators in effective field theories. But if you just want to talk about the collinear sector, the only things you need are this chi-n, this bn field, and then p perps, and no other things.
That's to go just one order?
All orders.
So why aren't there any?
I'll talk about it. Yeah, we'll show you. I'll show you. Yeah. I mean, intuitively, you would think these are the physical degrees of freedom, right? There's two of them. So that's intuitive. But I'll show you how you get rid of all the other ones. So it kind of matches up with what you want. You could think that, you know, these are the physical gluons that you're producing, and your operators can be set up so that they only depend, that there's not so sort of any spurious components. Okay, so we'll get there. So let me introduce a bit of notation. I have to do. So let's consider this thing, a covariant derivative sandwiched with Wilson lines on either side. And this IDN here is like P bar plus so it just involves the collinear gluon field. So then if I have that operator and I just take n bar IDN, then that's P bar. If I take I dn perp mu, then you can show that this guy is p perp mu plus g bn perp mu. So this one is just a relation we talked about before. This one is not as obvious, but if you take this guy, you can either let the derivative, you can let this derivative p perp act on the Wilson line or act through. If it acts through, that's this term. If it acts on, then I can manipulate the operator so that it is exactly of this form. And part of that comes from the fact that I can explain it to you here. I have it in my notes, and you can look at it later, but let me just explain it in words. If you looked at the term in this commutator that was the other order, where the im bar dot d was sitting here, then it would hit the Wilson line, you get 0. So that term was just put in to make it look like a gauge field. I mean, a covariant, to make it look like a field strength. Okay, so really you have im bar dot d dn perp without the comma, without the brackets. But then this combination here is just, you can use the identity that we had with the, and basically if you push this guy through here, you're canceling the p bar. So it's just giving you the Wilson line. So that's basically how you go from here to here. Okay, so this is by way of arguing that I don't really need, if I'm considering this is basically what this is saying is I don't need to consider covariant derivatives because I can instead consider p perps and b perps, and that's equally good. Okay. Now, if you do a similar type of thing in the n component, then you can derive a similar type of object. So this is the same object as we have over here, but instead of having an I dn perp, I'd have an n dot d. So dn perp replaced to n dot d. And that looks like it could be something that you'd build operators out of. So why not, and also furthermore, why not have operators that depend on this n dot partial? Okay. So for p bar, we don't have to worry about that. So okay, we have, I said we'll include this, we'll include that. I didn't say we'll include this, this, and this. So there's three things I have to argue away here. The derivatives that are p bars, those just go into the Wilson coefficient. So if we had like p bar chi n comma omega, for example, then that's omega chi n comma omega, and this is put into the Wilson coefficient. So that's why we don't have to worry about having p bars. In some sense, we do have p bars. They're all in the Wilson coefficients. So it's really these other two that we have to worry more about. And those actually can be simplified using the equation of motion. So if you have I n dot p on I n dot partial on chi n, then the equation of motion, when you write it out in terms of these objects, it has some form. And basically, you can just get rid of those terms. So equation of motion allows us to get rid of I n dot partials that are on chi n's. So that's why we don't have to worry about those. And this is just like saying that in our leading order action, there was an I n dot partial. And that's just like saying there was time derivatives in our leading order action in some standard effective field theory. But then in the higher dimension operators, you can always use the equations of motion to get rid of those time derivatives. And here we're using the equation of motion to get rid of I n dot partial. So it appears in the leading order action, but then we don't have to have it in any other subleading operator, and that's why it's not one of the ones that's included in the list. And if you had I n dot partial on curly B, that's also a part of the equations of motion of the gluon field. Now, when you do the gluon equations of motion, there's components, because it's a vector. And one of the other components allows you to get rid of the n dot b. So there's another term that you can rearrange. And I won't write it out because the equation's rather messy, but give you some idea. There's another component that looks like this, where I can get rid of all the n dot curly b's using the gluon equation. So the gluon equations of motions allows me to get rid of both of these things. And then I just have and basically after I've done that, I just have the objects that I've told you we can use. So after using equations of motion, we can get down to those objects. And any other thing that you might dream up can be reduced to these objects. So I'm not saying that I went through a complete list here. For example, what if you had a commutator of two dn perps? Right? You might say, oh, that's some new thing. It's not. It's one of these. You can also reduce that too. Let me list that one just to give you some idea that there's others you might think of dreaming up. So you can reduce all others to this set. Okay, so for the collinear sector, this is enough for to build higher dimension operators, just these three. And then for the ultrasoft sector, so I guess this is 2. We do need ultrasoft ultrasoft derivatives. And ultrasoft field strengths. And ultrasoft quarks. So this part is really just similar to the story that you'd have for a standard low energy effective field theory, like integrating out a massive particle. You can use the equation of motion. One thing that is worth commenting about is the connection between 1 and 2. So 1 is collinear and 2 is ultrasoft. And a priori you might think, well, they're totally independent. But we saw last time that reparametrization invariance connects them. So if I've decided that this is the type of basis I want to use for my operators, then what is the reparametrization connection? You can rewrite what we said last time in terms of these curly Ds, because it basically just means moving the Wilson lines that we had in this formula last time. They were around the ultrasoft operator last time. And if I just move them over to the collinear operator, then I get this curly D. Right? So the RPI connection is connecting the curly D to the D ultrasoft, curly D collinear to the D ultrasoft. And then you can write this guy as the P perp plus the B perp. Okay, so that's, and likewise, if you do the same for the N-bar sector, you move the Wilson lines from this term to that term, then it looks like these two combinations. So that's just rewriting what we had before, but now in terms of this type of notation. Okay, so that's enough to build operators at higher order. And then we write down Wilson coefficients for those operators that are functions of a large momentum, and then we start doing physics with them. So any questions about that?
For the equation of motion,
Yeah.
You always just use the leading order equation of motion
Yeah.
into higher order term.
Yeah, these are the L0 equations of motion. That's what I'm doing here, writing here. Yeah, there's one more actually. There's 3 that it's only needed at some very high order, but.